Hello guys, welcome on Tesla Eduventures. In this video today we are going to discuss the kinetic theory of gases and we are starting the KTG and thermodynamics section. So in the kinetic theory of gases there are some assumptions about the visualization of an ideal gas, which means that on the basis of these points you can visualize the properties and characteristics of an ideal gas. So these are just assumptions, and obviously we believe that the ideal gases do not exist in nature, but we can say that at certain physical conditions real gases can behave like ideal gases. Okay, so the first assumption of kinetic theory of gases is the fact that an ideal gas has very large number of molecules, and these molecules are hard and elastic spheres which collides with each other and with the walls of the container elastically, which means that let's suppose that there is a cubical vessel and the gas is filled in this vessel, and the molecules are colliding because of due to the fact that they have random kinetic energy, and this kinetic energy is due to the room temperature. So due to that kinetic energy they are randomly moving here and there, and they are colliding with each other, and they are colliding with the walls of the container, and these collisions are elastic collisions, which means that E is equal to 1 and there is no loss of energy in this type of collisions. Okay, now loss of kinetic energy obviously. Now let us see the other case that we know that most of the part of the gas, or most of the volume of the gas is empty, which means that if we collect all the molecules individually from the gas and we make them we place them very close to each other and we make a plum pudding of them, then we would see that the total volume of those all molecules will be only 0.014% of the volume of the gas, which means that if the total volume of the gas is measured, or if the total volume of the molecules is measured as compared to the volume of the gas, then this volume of the molecules is very negligibly small as compared to the volume of the gas, which means that in gas these molecules are very far away from each other, and they are very farly spaced, and we can say that most of the part of the gas or most of the volume of the gas is empty. Now in the third part, that ideal gas do not have any specific shape or size or volume. In fact, the shape, the size and the volume of the container is the volume or the shape of size of the ideal gas. Obviously you can see that if this ideal gas is contained in this cubical vessel, then you can see that its shape would be cubical, its volume will be a cube, which is the volume of the cube, and if it is contained in a sphere, then its shape would be spherical and its volume would be 4 pi r square. So volume, shape and the size of the ideal gas depends on the size, volume and shape of the vessel. Now you can see that the molecules do not move in some preferred direction of motion. In fact, their motion is completely random and they do not move in a straight line, which means that the molecules have thermal kinetic energy, and therefore they are not moving in a straight line because that thermal kinetic energy gives them a random velocity which can be in any direction. Okay, so and also due to the fact that there is no perfectly empty space in the container, these molecules are facing the collisions with other molecules in their way, and after collisions they are moving in the random directions. So you can see that this path of the molecule can be governed by the Brownian motion, in which it is stated that the molecules move in a zigzag path, which is not a straight line path, and the distance traveled by a molecule between two successive collisions is called as the mean free path. So what we can say that this distance, this molecule is going in this direction, then it collides with this one, and then it goes in this direction, then it collides with this one, and so on. So the distance between two successive collisions is called as the mean free path, and later in some videos I would be calculating the value of mean free path. Now in the next point, it is stated that these molecules collides with the walls of the container and they transfer their momentum to the walls. This momentum transferred per unit time, per unit area of the wall is called as the pressure acting on the walls. When we say that gas pressure is P0 or gas pressure is P, then we are referring to a fact that the molecules inside that vessel in which gas is contained, or in a room in which gas is contained, are continuously moving here and there randomly due to the thermal kinetic energy. And when these molecules strikes the walls of the vessel, then they transfer their momentum to the walls, and the transfer of momentum per unit area per unit time is called as the pressure of the gas on the chamber or the vessel in which it is contained. Okay, so you can see that if this molecule is moving in this direction with the momentum of mv, and we know that the collision is elastic, so it is rebounded by the same momentum mv, so the change in momentum of this molecule will be 2 mv. And if we can say that dt is the time of collision, then the force acting on this wall will be dp by dt, which is change in momentum upon time, and this is coefficient of restitution, which is the collision coefficient, and that is 1 because it is elastic collision, and the pressure would be this force upon area. This pressure of the gas of the molecule is same on all the walls, whether that wall is vertically up, vertically down, or sidewards. So gas applies equal pressure on all the walls of the container in which it is contained. We are talking about the ideal gas. Now this is very important and very important point about the assumptions of an ideal gas, that we know that molecules collides, and when they collide they apply some contact force on each other, but apart from that force they do not interact with any other field force or any other force, and therefore we can say that there is no interaction force between the ideal gas molecules, and there is some interaction force between the real gas molecules. And due to the fact that there is no interaction between the molecules of an ideal gas, there is no internal potential energy of the ideal gas. In fact, the internal energy of an ideal gas is just the internal kinetic energy of the molecules and the vibrational energy of the atoms inside the molecules. This is very important conclusion, and there is a very hugely discussed confusion between the students about the fact that whether internal energy of an ideal gas is an absolute quantity or it is a relative quantity. In chemistry, they are being taught that internal energy of an ideal gas is a relative quantity, but in physics we teach them that internal energy of an ideal gas is absolute quantity. Now I will burst out this myth and I will make a bridging connection between these two concepts which are being taught differently in physics and chemistry. Now let us analyze the real gas. We have already discussed the fact that real gas molecules have kinetic energy, internal kinetic energy of the molecules, and they have the internal potential energy, intermolecular potential energy, which is due to the interaction forces between the two molecules. And these molecules are made up of atoms. If it is a diatomic, triatomic or polyatomic gas, then these atoms also vibrate inside the molecules, and there is a significant amount of vibrational energy of the molecules. But in the ideal gases, the kinetic energy, we know that ideal gases do not interact with intermolecular forces. Therefore, intermolecular potential energy in the ideal gas is 0, and therefore we can say that the only two energies in the ideal gas are kinetic energy of the gas molecules as well as vibrational energy of the gas molecules. Okay, now at low temperatures, at room temperature is a low temperature as far as the analytical part of thermodynamics is concerned. At room temperatures, we assume that the vibrational energies are so small so that we can neglect them, and they are not significant enough to be taken in the calculation. So at room temperature, at low temperatures, we always assume that the vibrational energy of an ideal gas is also 0. So at low temperature, the internal energy of an ideal gas is just the internal kinetic energy of the gas molecules, and their vibrational energy can be neglected. And obviously we already studied in the mechanics that kinetic energy is a absolute quantity. We can find out the kinetic energy of any individual mass or anything, and it does not depends on it is not calculated with respect to some point or some observer. So obviously this is absolute quantity, kinetic energy, and what I'm trying to say is the fact that I can I can say that if a mass is moving, if a 2 kg mass is moving with the speed of 2 meter per second square, then its kinetic energy would be 4 joules. So in this phrase, I do not have to mention that the kinetic energy change is 4 joule or something else. I can just say that its kinetic energy is 4 joule, which means that kinetic energy is a absolute quantity. But when we say that the potential energy of an object is mgh, then it should be mentioned that h is the height from the ground, or from that point where we have considered that the potential energy is 0. So obviously it means that the potential energy is a relative quantity which depends on the frame of reference. Now we can say that at higher temperatures, the vibrational energy of the atoms inside the molecules is not significantly small so that we can neglect it, and therefore we cannot ignore that vibrational energy, and we have to consider that vibrational energy in the internal energy calculations of the gas. And this is obviously on the high temperatures, and at high temperature the ideal gas has translational and rotational energies of the gas molecule and vibrational energy of the atoms inside the gas molecules, and therefore at higher temperatures the internal energy is the sum of the translational kinetic energy as well as the vibrational energy of the gas molecules. So we can say that vibrational energy is the energy of vibration or oscillation of the atoms inside the molecules, and we have already studied in SHM that the energy of SHM or vibration is the sum of energy of kinetic energy as well as potential, and potential energy we know is a relative quantity. So that is why at higher temperatures we can say that the internal energy of the gas is a relative quantity and it is not an absolute quantity. But until and unless it is stated in the question, we do not consider the high temperatures. Okay, if they wish that we should consider the vibrational energy, they would mention the temperature is high or high temperatures in the question separately. Now the motion of the gas molecule inside the gas, inside an ideal gas, is governed by the Newton's laws of motion, and we do not consider any effect of gravity on the molecules. Okay, this is the fact, because if we would consider the effect of the gravity on the molecules, then we would not say that the pressure on the bottom and pressure on the top of the vessel faces is same. Because if we would consider the gravity, then we would say that molecules will strike this bottom surface with some higher velocity. But that is not the case. We do not consider any gravity effect on the molecules. And you can think that the major fact or the major difference between the ideal gas and the real gas molecules is the fact that the real gas molecules interact with each other with the intermolecular forces, due to which they possess some intermolecular potential energy. But a real gas do not interact with the intermolecular forces, and therefore they do not possess any intermolecular potential energy. Therefore, what we can say that if a real gas is taken at higher temperature and lower pressure, so at higher temperature the kinetic energy of the gas molecules would be higher and they would run away from each other in the different directions, and at lower temperatures the kinetic energy of the gas molecule, and lower pressure the molecules are being not pressed or are being not forced to situate closer to each other. So we can say that at higher temperature and at lower pressure the conditions are created such that molecules are far away from each other, and due to the fact that molecules are far away from each other, they are not able to interact with any intermolecular forces between them, and therefore there is no intermolecular potential energy of the gas molecule, and hence we can say that a real gas can behave to 99% or 98% as ideal gas at very high temperature and at very low pressure. Okay, now let us see that what is the difference between an ideal gas and a real gas. So by mathematically, so by equation, so you must have seen this real gas equation somewhere. So you can see that this is P plus A n square by V square into V minus NB, and that is equal to nRT. So this A and this B are the van der Waals constants. These are generated due to van der Waals intermolecular forces between the gas molecules, and N is the number of moles, V is the volume of the gas, and R is the gas constant, and T is the temperature of the gas, absolute temperature, which is the temperature in Kelvin. So we know that if we are talking about the ideal gas, then the van der Waals forces are not present in the ideal gas. So we can say that in an ideal gas A and B are 0. So if A and B are 0, then this equation simplifies into PV is equal to nRT. This is the equation for an ideal gas, and obviously in complete thermodynamics of JEE we are studying the properties of an ideal gas, so we would be using this equation as our base equation, that PV is equal to nRT. So guys, these were some points which on which you can imagine the existence of an ideal gas, or these are the points on which you can confirm the transformation of a real gas into ideal gas. So in the next video I would be bringing some more concepts about an ideal gas. Thank you.